An introduction to artificial intelligence. From ancient myths of mechanical men to the modern marvels of self driving cars, humanity has long been fascinated by the idea of creating artificial intelligence. Today, we stand on the precipice of a new era where AI is not just a dream, but a reality that is fast transforming our world. Join me as we trace the evolution of AI from its early beginnings to its current state of the art. The talk is outlined in three parts, starting with an introduction to AI and some core and general concepts that go into building the beast. When we talk about the specific paradigm that has yielded almost all the amazing progress we have seen recently, we end with a brief discussion on some applications, some ethical concerns, and some related issues, with the hope that this brief introduction prompts the listener to form their own mental models of a technology that has the potential to change our world more radically than electricity, fire, the printing press, and the internet collectively did. With that, let's dive right in. Introduction Part 1. Unveiling the Enigma. Intelligence is the cornerstone of human cognition and encompasses our ability to learn, reason, problem solve, perceive our environment, plan, and even express creativity. In the realm of machines, artificial intelligence aims to replicate or even surpass these cognitive functions. It is about creating systems that can exhibit intelligent behavior, whether that involves making decisions, understanding language, or recognizing patterns. AI can be placed upon a spectrum, just like human intelligence in general can be placed on a spectrum. We started out with building narrow AI systems, which are the most prevalent forms of AI. These systems are designed to excel at specific tasks within a limited domain. Think of a chess-playing AI like Deep Blue, or a voice assistant like Siri that can answer question answers and set reminders. These systems operate within predefined boundaries and lack the ability to generalize the knowledge to new situations. Opposed to this is general AI, or strong AI, which some people also label AGI. This represents a holy grail of AI research, a hypothetical machine with human-level intelligence across a wide range of domains. An AGI would possess the ability to reason, learn, and adapt to new challenges, much like a human being. While AGI remains a theoretical concept, its development raises profound questions about the nature of consciousness and the future of humanity. Let's dispel some misconceptions before diving deeper. AI is not the same as robots. While robots are often associated with AI, it is important to remember that AI is fundamentally about software and algorithms. AI algorithms can power a wide range of applications, from self-driving cars to medical diagnosis tools, without necessarily involving physical robots. The best metaphor to use over here would be the human creature. We are made up of two parts which are disjointed, which are also connected holistically, the mind and the body. The hope is the mind can live outside of the body, and that the body can operate without having a mind. And you can think of a robot as being that body, and the AI being the mind. When you bring them together, you get an embodied AI, an embodied AGI. The holy grail of all our efforts in this domain. It is also not the same as sentience. Despite portrayals in science fiction, AI systems today are not sentient. They lack emotions, consciousness, and self-awareness. They operate on data and algorithms, not on feelings or desires. And also, at this moment in time, AI is just a tool. It is not a threat. It's a tool that can be used for good or ill, depending on how it's designed and deployed. One of the godfathers of this domain was Alan Turing, who came up with the concept of the Turing test. A test which would allow us to glimpse into the nature of intelligence. He proposed the imitation game, which was a thought experiment that aimed to answer the question, can machines think? By focusing on the machine's ability to imitate human conversation. The test involves a human evaluator engaging in text-based conversations with both a human and a machine. If the evaluator cannot reliably distinguish between the two based on the responses, the machine is said to have passed the test. The Turing test has been highly influential in shaping AI research, sparking debates about the nature of intelligence and consciousness, has inspired the development of chatbots and conversational AI systems, which have become increasingly sophisticated over the years. While the Turing test remains a significant benchmark, it has limitations. It focuses on the machine's ability to mimic human behavior rather than truly understand or possess human-like intelligence. Modern AI research has moved beyond mere imitation and is exploring deeper questions about how machines can learn, reason, internalize information, and solve problems in ways that are both effective and ethical. Now let us talk about the branches of AI, the tools and techniques which are shaping the field. We start out with one of the core ideas at the beginning of our journey was the idea of symbolic AI, which we now call good old-fashioned AI, or GoFi. This was the rule-based era. The core idea here was that intelligence can be achieved by manipulating symbols, which can represent real-world concepts, and manipulating these according to explicit rules. It was akin to playing chess, where each move was governed by a set of well-defined rules. The methods used over here were logic programming, where we use formal logic to represent knowledge and infer new facts. Prolog is a classic example of a logic programming language. You used to also have expert systems, which would encode human expert knowledge in the form of an if-then rule system. These systems excel at diagnosing problems and offering solutions based on their rule-based knowledge. It also used a method called knowledge representation, which involved developing formalism for representing knowledge in a way that AI systems can understand and reason about. An example was Mycin, which is an early expert system developed in the 1970s to diagnose bacterial infections and recommend antibiotic treatments. It contained a knowledge base of hundreds of rules derived from medical experts. While groundbreaking at the time, Mycin's reliance on explicit rules limited its ability to handle the complexity and uncertainty of real-world medical scenarios. Symbolic AI is severely limited by its brittleness, for these systems struggle when faced with novel situations and incomplete information. They cannot easily adapt to changes or handle exceptions to their rules. They also have a very potent knowledge acquisition bottleneck. For encoding expert knowledge into usable formats is a labor-intensive and time-consuming process. This is something where we've come full circle, as we are now using deep learning systems to build these old-fashioned expert systems. The revolution started with what we now call machine learning, which at the start of it had different names. Some people used to call it data science, some people used to call it big data. Machine learning is about learning from data, not rules. The core idea is instead of relying on explicit rules, machine learning algorithms learn patterns and relationships from data. This allows them to make predictions, classifications, or decisions without being explicitly programmed for each scenario. The three major types of machine learning systems are supervised learning systems, where the algorithm is trained on labeled data, where the correct answer, for example, dog or cat or elephant or lion, is provided for each example. The goal then is to learn a general rule that maps inputs to outputs in the case of image recognition systems, looking at the features that cats possess, and then mapping it onto dog or cat objects. The second system is called unsupervised learning, where the algorithm is given unlabeled data and must discover patterns or structures within it. Common tasks include clustering, which is grouping similar data points, and dimensionality reduction, which is simplifying data. And the third method, which is commonly used for robotics, is reinforcement learning, where the algorithm learns by interacting with an environment and receiving rewards or penalties for its actions. It aims to maximize its cumulative rewards over time. These systems, when implemented over multiple layers, becomes known as what we call deep learning. The idea here is that we use artificial neural networks which have multiple layers of the systems that we just spoke about to learn hierarchical representations of data. Deep learning exploded into public consciousness with the ImageNet breakthrough in 2012, where a deep neural network called AlexNet won the ImageNet competition. This victory demonstrated the power of deep learning and sparked a renaissance in AI research. The applications, some of the core applications are image and video recognition. Deep learning has revolutionized computer vision, enabling applications like facial recognition, object manipulation and detection, and self-driving cars. Natural language processing. The deep learning models like GPT-4, Gemini Pro have achieved remarkable results in language translation, text generation, and conversational AI. Speech recognition, where deep learning has improved the accuracy and robustness of speech recognition systems, powering virtual assistants and transcription services, getting us to the closer to the goal of universal real-time translation. Let's go a bit deeper into reinforcement learning, which is predominantly used to master complex environments, chaotic environments, ever-changing environments. The idea is that agents learn by interacting with an environment and receiving feedback in the form of rewards or penalties. The goal is to develop a policy that maximizes the agent's expected cumulative rewards over time. An example here is AlphaGo, which is developed by DeepMind, which used reinforcement learning to master the ancient game of Go, defeating the world champion in 2016. This was a major milestone, as Go was considered far more complex than chess and beyond the reach of traditional AI methods. It is used in a wide range of applications, including robotics, predominantly in robotics, but also in game playing, resource management, and even drug discovery. Let's dive a bit deeper into neural networks, which are the building blocks of the revolution that we are seeing. Neural networks have been inspired from nature, inspired from the neural nets that we have. There are vast differences between the two. The neuron, found in our brains and the brains of all living entities, except for the super simple ones, are found in the human brain, and they are a marvel of biological engineering, as it consists of an intricate network of interconnected neurons, leading to a kind of complexity that one could not imagine having. Each neuron acts as a miniature information processor, receiving signals from other neurons, integrating those signals, and transmitting new signals based on its internal states. This biological blueprint provides inspiration for artificial neural networks, ANNs, which are the fundamental building blocks of deep learning. The analogy is that the neurons, the dendrites in our brains, can be considered to be the inputs for neural networks. For they are similar to how dendrites receive signals from neighboring neurons. And just like that, artificial neurons receive numerical input, which could be a raw data stream like pixel values in an image or words in a sentence. Weights and synapses. Each input is associated with a weight, a numerical value that determines the strength of the connection between neurons. Larger weights signify stronger connections, indicating that the input is more important. Activation function and cell bodies. The neuron's cell body processes the incoming signals by summing the weighted inputs and applying an activation function. This function introduces nonlinearity, allowing the network to learn complex relationships in the data. Common activation functions include ReLU, or rectified linear units, sigmoid, and more. Output in axons. The result of the activation function is the neuron's output, which is then translated along its axon to other neurons in the network. The simplest neural network is the perceptron, which is a single artificial neuron that can be trained to make binary classifications, cat versus dog, spam versus not spam. It takes multiple inputs, each weighted differently, and produces a single binary output based on whether the weighted sum of the input exceeds a certain threshold. Multi-layer perceptrons. While perceptrons are limited to simple linear classifications, MLPs can learn complex non-linear relationships by stacking multiple layers of neurons. MLPs consist of input layers, which receives the raw input data, hidden layers, where the learning of the abstract representations of the data happens, and the output layer, which produces the final prediction or classification. It can be considered to be universal approximators. For MLPs with enough hidden layers and neurons can theoretically approximate any continuous function, making them powerful tools for modeling complex data. Backpropagation. It's a key algorithm that enables neural networks to learn from their errors. It relies on the chain rule of calculus to calculate how much each weight in the network contributes to the overall error. And using an optimization algorithm like gradient descent, it iteratively adjusts the weights to minimize the error. Backpropagation is computationally efficient, making it feasible to train large neural networks on massive datasets. Activation functions. Without activation functions, neural networks would be limited to performing linear transformations, making them incapable of modeling complex real-world phenomena. Activation functions introduce nonlinearity into the network, allowing it to capture complex patterns and relationships in the data. An example is the ReLU, which is simple, efficient, and widely used in hidden layers, sigmoid, hyperbolic tangent, and softmax. Now let's talk about training a deep neural network, which in common terms could be considered to be building a brain, or building a neural network. Building a neural network is just the first step. To unlock its full potential, we need lots of data, and good, high-quality data, allowing it to learn patterns from this data and make accurate predictions. The training process starts from this data collection and pre-processing, which is the first step, where the first step is to gather a large, contextual and diverse data set relevant to the task at hand. This data set needs to be cleaned, labeled for supervised learning, and pre-processed to ensure consistency and quality. The input data is fed into the network, and the neurons in each layer perform their calculations, passing the results to the next layer until the final output is produced. The output of the network is compared to the ground truth, the correct answer. The loss function is used to quantify the error. The error is propagated backwards through the network, and the weights of each neuron are adjusted to minimize the loss. The process is repeated iteratively for many epochs, which are the passes through the entire dataset. Various optimization algorithms such as stochastic gradient descent or ADAM are used to guide the weight updates and help the network converge to a solution that minimizes the network's performance is evaluated on a separate validation set to tune hyperparameters and to prevent overfitting. Finally, the model's accuracy is assessed on a test set to estimate its real-world performance. Some challenges in training. During backpropagation, the gradients or error signals can become very small, vanishingly small, or very large, hindering the learning process. Techniques like gradient clipping and specialized architectures like LSTMs are used to mitigate these issues. Overfitting, where the model memorizes the training data too well, performing poorly on unseen data. This is addressed through regularization techniques like dropout and early stopping. Hyperparameter tuning, where we find the optimal values for hyperparameters like the learning rate and the batch size. This can be time consuming and requires careful experimentation. Training resources. Training deep neural networks requires significant computational power, especially for larger models and data sets. GPUs or graphics processing units are commonly used to accelerate the training process. Cloud-based platforms like Google Colab and Amazon SageMaker provide accessible resources for training and deploying deep learning models. Architectures for different tasks. 1. Convolutional neural networks. They're specifically tailored for processing grid-like data, such as images and videos, where spatial relationships between pixels are crucial. The key components are the convolutional layers. These layers apply filters, also called kernels, to small patches of the input image, extracting local features like edges, corners, and textures. These filters are learned from the data, allowing the network to discover the most relevant patterns for the task at hand. Pooling layers. These layers reduce the spatial dimensions of the data by summarizing the information from neighboring pixels. This helps to make the network more computationally efficient and less sensitive to small variations in the inputs. Fully connected layers. These layers integrate the extracted features from across the entire image and produce the final output, such as a classification label or object bounding boxes. Applications. The CNNs have revolutionized computer vision, enabling breakthroughs in image classification, such as accurately categorizing images into different classes. Object detection, such as identifying and localizing multiple objects within an image or video. Facial recognition, such as identifying individuals based on their facial features. And medical image analysis, where we diagnose diseases from X-rays, CT scans, and other medical images. Recurrent neural networks and LSTMs. These RNNs are designed to process sequential data where the order of the elements matters. This includes text, speech, time series data, and music. Memory and feedback. RNNs have a unique structure that allows them to maintain a hidden state, a form of memory that carries information from one step in the sequence to the next. This allows them to capture dependencies between elements across time. Long short-term memory. A special type of RNN designed to address the vanishing gradient problem, which can hinder RNNs from learning long-term dependencies. LSTMs have a more complex internal structure with gates that control the flow of information, allowing them to remember information for longer periods. RNNs and LSTMs have been successful in language modeling, machine translation, sentiment analysis, and speech recognition. Generative adversarial networks, GANs. Two networks in competition. GANs consist of two networks working in tandem. The generator network, which tries to produce realistic data, such as images or music, that can fool the discriminator, and the discriminator network that tries to distinguish between real data and data generated by the generator. The adversarial game, since these two are trained together in a competitive process, the generator gets better at producing realistic data, while the discriminator improves at detecting fakes. This adversarial game drives both networks to improve continuously. Applications. GANs have shown remarkable results in image generation, such as creating photorealistic images of faces, objects, and scenes. Image-to-image translation, transforming images from one side to another, turning a daytime photo into a nighttime photo, for example. Text generation and music generation. Transformers. Attention is all you need. The transformer architecture, introduced in 2017, has revolutionized NLP tasks. The self-attention mechanism, instead of processing words in a sense sequentially, transformers use self-attention to weigh the importance of different words in relation to each other. This allows them to capture long-range dependencies and contextual information more effectively. Transformers are highly parallelizable, meaning they can be trained on massive datasets using powerful GPUs. This has led to the development of large language models like GPT-4, which have demonstrated impressive capabilities in language understanding and generation. The applications of transformers have predominantly been in machine translation, text generation, question answering, and code generation. AI in the real world and the future. Let's talk of some core applications of AI. Healthcare, where it has assisted in diagnosis, where AI systems can analyze medical images, help detect diseases, often with accuracy which is better than human experts. Drug discovery, as accelerating the process of discovering new drugs by analyzing vast amounts of data, simulating molecular interactions, and predicting the effectiveness of potential treatments. Personalized medicine, where AI can tailor treatment plans based on individual patient data, genetic information, and lifestyle factors, leading to more effective and targeted therapies. Finance. High-frequency trading algorithms execute trades at lightning speed based on complex patterns and market signals, potentially impacting market volatility. Fraud detection. AI systems can monitor transactions and identify anomalies that might indicate fraudulent activity, protecting both financial institutions and consumers. Customer service chatbots. AI-powered virtual assistants can handle routine and customer inquiries, freeing up human agents to focus on more complex issues. Transportation. Self-driving cars. Autonomous vehicles have the potential to revolutionize transformation, improving safety, reducing traffic congestion, and increasing accessibility, also improving the quality of life. Traffic optimization, where AI algorithms can analyze traffic patterns in real time and adjust traffic signals to optimize flow, reduce commute times, and fuel consumption. Entertainment, recommendation systems. Netflix, Spotify, YouTube, and other platforms use AI to analyze user preferences and suggest content tailored to individual tastes. Content generation. AI can now generate music, artwork, and even scripts for movies and TV shows. Before long, it will also be able to generate entire movies and books that are better than the best of human quality. AI has applications in agriculture, education, and climate change mitigation, and so much more. You can think of AI as being our silver bullet for all our problems. It's the final invention of humanity. I want to briefly touch upon the black box issue, the explainability problem. The issue is that many advanced AI models, especially deep learning models, often considered black boxes. The decision-making processes are so complex and opaque that even their creators may struggle to understand why they arrive at specific conclusions. This lack of transparency is particularly problematic in high-stakes domains like healthcare, finance, law, and decision-making, where understanding the reasoning behind decisions is crucial. Explainable AI, or XAI, is a growing field of research aimed at developing techniques and tools to make AI models more interpretable. This includes methods like local interpretable model agnostic explanations, or LIME, shapely values, and attention mechanisms. Robustness and safety. Adversarial examples are terribly designed inputs that exploit vulnerabilities in AI models, causing them to make incorrect predictions. Even small, imperceptible changes to an image or text can fool even state-of-the-art models. Real-world consequences. Adversarial attacks pose significant risks, especially in safety-critical systems like autonomous vehicles or medical diagnosis tools. Data privacy. Large data sets are essential for training powerful AI models. However, these data sets can contain sensitive personal information, raising concerns about privacy and potential misuse. Privacy preserving AI. Techniques like differential privacy and federated learning aim to enable AI development while safeguarding individual privacy. Differential privacy adds carefully calibrated noise to data, making it difficult to identify individuals while still allowing for meaningful analysis. Federated learning trains AI models across multiple decentralized devices, keeping the data local, only sharing model updates. Bias and fairness. Let's now talk about some of the societal considerations. Bias and fairness. Data-driven bias. AI systems learn from historical data, which can reflect societal biases and inequalities. This can lead to discriminatory outcomes in areas like hiring, lending, and criminal justice. Algorithmic amplification. Even small biases in data can be amplified by AI algorithms, leading to significant disparities in outcomes for different groups. Addressing bias requires careful data collection and curation, algorithmic transparency, and explainability in AI, ongoing monitoring and evaluation. Job displacement. Automation and the workforce. AI and automation have the potential to displace jobs in various sectors, from manufacturing and transportation to customer service and data entry. As AI takes over routine tasks, the demand for higher level skills like creativity, critical thinking, and emotional intelligence will increase. Preparing for the future. Education and workforce development programs need to focus on reskilling and upskilling individuals to thrive in an AI-powered economy. Autonomous weapons. The rise of killer robots. AI weapon systems can select and engage targets without human intervention, and this raises serious ethical concerns. The loss of human control. The potential for unintended consequences and escalation of conflicts and violation of international humanitarian laws. Global regulation. International efforts are underway to establish regulations and bans on autonomous weapons, just like humanity got together to ban all chemical weapons. Existential risk. Superintelligence. A hypothetical AI system with an intelligence far surpassing that of the brightest humans. This is one of the holy grails of AI labs operating around the world, such as Safe Superintelligence Institution, which Elias Sutskever just started a couple of weeks back. The control problem. Concerns about the potential for superintelligence to become uncontrollable, leading to unforeseen and potentially catastrophic consequences of humanity, are one of the things which keep many experts awake at night. Responsible AI development, where we need to emphasize aligning AI goals with human values, ensuring safety measures, and establishing ethical guidelines to mitigate potential risks. Let's briefly touch upon the quest for AGI, which is the ultimate goal of creating machines with human-level intelligence across a wide range of tasks and domains. There's a significant debate about the feasibility and the timeline of achieving AGI, as well as its potential impact on society and the future of humanity. Developing AGI raises profound questions about consciousness, ethics, and the potential for unintended consequences. The role of humans and AI collaboration. Human-in-the-loop AI. This method emphasizes the collaboration between humans and AI systems, where humans provide domain expertise, judgment, and oversight, while AI assists with tasks that require speed, accuracy, and data analysis. AI can enhance human abilities, leading to new levels of productivity, creativity, and problem solving. As AI continues to automate tasks, It's crucial to focus on reskilling and upskilling the workforce to adapt to new roles that emphasize uniquely human qualities like creativity, critical thinking, and emotional intelligence. The way forward: ethical AI development, where we need to prioritize fairness, transparency, and human oversight in the design and deployment of AI systems. Public engagement, which involves diverse stakeholders in discussions about the impact of AI and the development of ethical guidelines, and educating and making people aware, making the public aware of AI's potential, its benefits, its risks, its implications, and empowering individuals to make informed decisions about its use. The end. As we conclude this shallow deep dive into artificial intelligence, it's clear that we stand at the threshold of a new era, one where machines are no longer just tools but partners in our quest for knowledge, innovation, and progress. AI has the potential to solve some of humanity's most pressing challenges, from curing diseases to combating climate change, but it also raises profound questions about the nature of intelligence, consciousness, about the risk-reward calculus we've been operating by, and the very definition of what it means to be human. The choices we make today about how we develop and use AI will shape the trajectory of our species, of our future. We must embrace its technology with a sense of both wonder and caution and responsibility, ensuring that it's harnessed for the betterment of humanity, not its greed or detriment. By fostering a deeper understanding of AI and its potential impact, we can navigate this uncharted territory with wisdom, responsibility, and a shared commitment to a brighter future for all.